Could the quantum internet revolutionize communication as we know it? As we journey into the realm of quantum networks, we find a world where qubits, the fundamental units of quantum information, hold the key to unparalleled advancements in both computing and communication. Unlike classical bits, qubits enable the complex dance of quantum entanglement, allowing information to be transmitted over long distances without losing its integrity. This feature is crucial for constructing quantum processors that can tackle problems once deemed impractical for classical computers. By linking quantum processors through sophisticated networks, we create computing clusters that increase computational power. In practical terms, this means networked quantum computing can solve specific problems, particularly those involving quantum system modeling, with unprecedented efficiency. Much like connecting multiple classical computers to form a supercomputer, quantum networks increase the potential of individual quantum processors. The magic lies in their ability to simulate quantum phenomena that classical machines cannot match, providing a glimpse into a future where complex calculations become routine. However, the success of this quantum network relies on more than just powerful processors. It hinges on the seamless transmission of qubits over long distances, a feat made possible by technologies like quantum repeaters and optical switches. As we delve deeper, we uncover the intricate dance of photons and atoms in quantum communication lines, setting the stage for a revolution in secure communication and beyond. But what challenges lie in achieving this quantum leap? In the world of quantum networks, connecting multiple quantum processors into a cohesive cluster transforms the landscape of computational power. By linking these processors through short-distance quantum networks, we form a distributed quantum computing system. This is similar to classical computing clusters, where several less powerful computers collaborate to form a single, more potent processing unit. Each connection between quantum processors allows qubits, the fundamental units of quantum information, to flow and interact across the network, enhancing the overall computational potential. This method amplifies the ability to solve complex problems, particularly those suited to quantum computing, such as simulating quantum systems. Unlike their classical counterparts, these quantum networks are capable of handling tasks that require significant computational power by simulating more qubits than classical computers can manage. As we continue to develop these systems, scalability remains a crucial advantage, allowing for the addition of more processors to constantly expand capabilities. However, this journey is just beginning, with current networks limited to short distances. As we explore further, imagine a world where these local networks evolve into a global quantum internet, an innovation that could redefine how we secure and transmit information. But before we can dream of a quantum World Wide Web, we must first conquer the challenges of long-distance quantum communication. Quantum communication unfolds through the intricate dance of qubits over vast distances, forming the backbone of the nascent quantum internet. Much like classical networks, quantum networks connect quantum processors, but with a twist. Entangled qubits transmit information with unprecedented fidelity. These qubits journey via optical fibers, retaining their delicate quantum states through the careful orchestration of interferometers and beam splitters. Here, standard telecom fibers are repurposed, carrying not just mere signals, but the whispers of quantum entanglement. At each juncture, quantum processors act as vigilant sentinels, receiving and transmitting quantum information. These processors can be modest, often just a single qubit, yet they wield the power to perform quantum key distribution. Through entanglement, even a solitary qubit becomes a conduit for secure communication. The magic lies in how these entangled qubits overcome distance. Unlike classical repeaters which amplify signals, quantum repeaters preserve the qubit state integrity, a feat enabled by the fundamental rules of quantum mechanics. This revolutionary approach ensures that the quantum internet can expand, linking nodes across the globe. As we unravel the secrets of quantum communication, we edge closer to a future where information flows with unparalleled security. But the journey doesn't stop here. Up next, we delve into the potential of harnessing these quantum networks for unprecedented computational power. In the heart of quantum internet architecture, we find end nodes equipped with quantum processors. These processors, even with just one qubit, can enhance quantum communication. Acting as the essential building blocks, they are where the magic happens. Applications are executed, calculations are processed, and information is stored with an unparalleled fidelity. Imagine a small quantum processor harnessing powerful capabilities to store and retransmit data without disrupting its quantum state. This is achieved through sophisticated systems like color centers in diamond or ion traps with entangled photons, creating pathways for quantum teleportation and remote entanglement. Communication lines form the lifelines of this network, utilizing existing telecom fibers. These fibers, familiar yet transformed, allow qubits to traverse distances without losing their delicate quantum nature. Optical networks are key, reducing the chance of decoherence and reusing infrastructures already in place. Essential to this setup are optical switches, preserving the coherence of the qubits, ensuring they reach their intended destination. Then, at the heart of long-distance communication lie quantum repeaters. These devices overcome the no-cloning theorem, a unique challenge in quantum transmission, by enabling information to leap vast distances without amplification. The mysteries of these repeaters lead us to consider what other barriers they might break, as we explore how the quantum internet could reshape our digital landscape. Quantum repeaters are central to overcoming the limitations posed by the no-cloning theorem, which prohibits the copying of quantum information. Unlike classical repeaters that amplify signals, quantum repeaters rely on entanglement swapping and quantum error correction to extend the reach of quantum communication. By preserving the delicate state of qubits, they enable the transmission of quantum information over distances far beyond the current limits of quantum processors. Here, quantum repeaters act as bridges, linking together quantum processors within this novel network. The intricate design of quantum repeaters ensures that qubits maintain their coherence and entanglement over long stretches of optical fiber. This is achieved through sophisticated end nodes, which can store and process quantum information without disturbing its intrinsic state. Technologies like nitrogen vacancy centers in diamond and ion traps play a crucial role, offering robust platforms for these repeaters. They not only facilitate the retransmission of qubits, but also enable quantum operations necessary for network functionality. As we stand on the brink of a quantum internet, these repeaters do more than just extend connections. They redefine what's possible in communication, making secure global quantum networks a tantalizing possibility. Next, we delve into the transformative potential of these networks and the unprecedented opportunities they unlock for global communication. As we dive deeper into the role of end nodes within quantum networks, we uncover their pivotal function as quantum processors. These processors, capable of receiving and emitting information, form the backbone of quantum communication systems. At their simplest, end nodes can be mere beam splitters and photodetectors, facilitating quantum key distribution with remarkable efficiency. But when the demands for advanced processing arise, more sophisticated systems step in. Imagine these as small quantum processors, capable of storing and retransmitting quantum information without altering the original quantum state, a task that demands precision and innovation. Take, for instance, the nitrogen vacancy centers in diamonds. These are not just theoretical constructs, but tangible systems that can operate at room temperature, performing small-scale quantum algorithms and even achieving quantum teleportation. And then there are ion traps, using magnetic fields and lasers to weave a complex web of quantum entanglement across nodes. Meanwhile, cavity quantum electrodynamics enables the seamless transfer of quantum states between isolated atoms, showcasing the true marvel of transporting quantum information. As these end nodes evolve, they pave the way for networks that are not just capable of local connections, but also of bridging vast distances. Up next, we explore how these quantum networks might redefine the very fabric of global communication, setting the stage for a revolution in how we connect across the world. Carry classical and quantum signals simultaneously, leveraging existing infrastructure to advance this quantum leap. Now let's delve into the intriguing world of innovative platforms, where diamonds and ions come into play. Nitrogen vacancy centers in diamonds offer a fascinating solution. These defects in the diamond lattice act as tiny quantum processors, capable of operating at room temperature. Here we see remarkable small-scale quantum algorithms and error correction in action. They've even demonstrated quantum teleportation between processors, a feat that could redefine how we understand remote entanglement. Similarly, ion traps represent another promising frontier. By using radio frequency magnetic fields and lasers, these systems manipulate ions to serve as qubits. Through a technique known as cavity quantum electrodynamics, quantum states can be transferred between atoms, creating remote entanglement. This allows for the seamless transfer of quantum information across distances, paving the way for a potential quantum internet. These platforms not only enhance our understanding of quantum mechanics, but also push the boundaries of what's possible. As we look forward, one question emerges: how will these breakthroughs influence the development of a fully functional quantum internet? Join us in the next chapter as we explore the potential impact of this revolutionary technology on global communication. Connect different quantum processors, enabling the practical realization of quantum networks. Photon-based qubits are pivotal in reducing the risk of decoherence, a phenomenon where quantum information is lost due to interaction with the environment. By leveraging existing optical fibers, these networks can harness established infrastructure, significantly lowering the barriers to building sophisticated quantum communication systems. Moreover, the use of single-mode fibers facilitates highly precise communication, essential for maintaining the quantum states required for entanglement. Entangled photons, pivotal in quantum protocols, can be reliably generated within these networks. The adoption of optical networks not only makes quantum communication feasible, but also scalable, allowing for the gradual expansion of a quantum internet. As we consider the transformative potential of these optical networks, we must ask ourselves, how might this foundational technology reshape the way we understand and engage with information in the quantum age?